Hello, everyone. I wanted to go through in a little bit of detail some examples of writing nuclear equations. This will be probably the most important concept for you to have mastered for the chapter on nuclear chemistry. So there are four examples here, and it asks us to write the nuclear equation for each of the following. So the first one is beta decay of xenon 133, and we're writing the nuclide here in this fashion that is only showing the symbol and the mass number. But in order to write a nuclear equation, we need to show the mass number as well as the atomic number. So I'm going to start with, okay, we know it's xenon, and we know that it is 133. We also need to know the atomic number. So we have here a periodic table, and so we look for xenon, and we see the atomic number of xenon is 54. So we would go ahead then and put that as the atomic number for the xenon. So that's what we're starting with. For all of these nuclear equations, well, I shouldn't say all of them. For this one, we're starting with only one reactant. So we can go ahead and draw the arrow showing how we change from that reactant. And in this case, we have beta decay. So we need to know what beta decay means. Beta decay means it's essentially losing an electron. So we can show that like this. So a beta particle has a zero mass number and has an atomic number of -1 because it is essentially equal to an electron. So the beta decay, and then the thing we're trying to figure out then is what else do we form? What is the other part of that? So this is where we go ahead and balance the nuclear equation based on the mass number and the atomic number. So we have 133 as a mass number here. Over here we have a 0. So this has to be 133. Okay, so 133 plus 0 equals 133. This is a 54. Here we have a -1. So we would have 55 plus -1 equals 54. So that's how we would go about checking that. And then we, again, look on the periodic table. I'm not going to go back to the periodic table every time, but you would look for the atomic number 55, and you would see that is CS, which is cesium. So you would figure out the symbol because you know what the atomic number is. Okay, so that's the first one. Let's move on to the next one. We would start in a similar manner. We would start in a similar manner by writing the nuclide in the form that we use for a nuclear equation. So the symbol is Rb, the mass number is 82, and then we would look up on the periodic table for Rb what is the atomic number. Rb is rubidium, and we would find that to be 37. Again, I'm not going to go to a periodic table every time, but you should know how to look on the periodic table to find those atomic numbers. And then as that is decaying, we look at, well, what type of reaction do we have here? Again, we have one reactant here. We know that we have a positron emission. So let's go ahead and write a positron. So positron has a positive charge, and it does not have a mass number. So mass number 0, atomic number of 1. For a positron. And then again, we get to the point of we have to figure out what is the new thing that we're making, and we figure that out by balancing the mass numbers and atomic numbers. So mass numbers here we have 0 plus what equals 82. Well, again, that's just going to be 82. And then down here we have 1 plus something equals 37. Well, 1 plus 36 is going to equal 37. So here we would look up on the periodic table what is the element with an atomic number of 36, and that is Kr, that is krypton. Actually, for this one, let me go ahead and go to the periodic table just because I want to point out a few things. So um, the 36 is right here. You'll notice that the mass number is not the same. These are average mass numbers, so make sure as you're looking on the periodic table, you're looking at the atomic number, that's the number above the symbol, as you are trying to identify it. The mass numbers will not, usually not be the same. So you shouldn't worry about the fact that here we have an 82, but on the periodic table, krypton had something like an 83. So that difference doesn't matter. Okay, let's move on to the next one. Here we have polonium. PO is polonium, 218. And then if you look on the periodic table, polonium has an atomic number of 84. So we write that there at the bottom. And then here we have alpha decay. Again, we have a situation where we have only one reactant. So we have this alpha decay occurring. So we need to remember, what is alpha decay? Alpha decay has a mass number of 4 and an atomic number of 2. And here I'm going to write the alpha symbol for that. So that is one thing, and then we have to figure out, well, what is the product? What else is forming here? And this is the first one where the mass number is not identical, right? So here we have a mass number of 4 for the alpha particle. 4 plus something adds up to 218. Well, that's going to be 214. And then down here we have 84, and then we have a 2. 2 plus something equals 84. Well, that is going to be an 82. So we check the periodic table, and we find atomic number of 82 is lead. And then the last one here is the electron capture by aluminum 26. Okay, so we can start by writing the, I'll go ahead and write it right here. Writing the symbol for aluminum 26, so mass number 26, symbol, and then we look up aluminum, atomic number is 13. Now, this one is different than the other three in that we actually have an additional reactant. So with electron capture, what's happening is that the nucleus is reacting with an electron. So we put that electron on the reactant side. Okay, so and then we go ahead and figure out our products. So our product here, mass number is still 26. And then atomic number, we have 13 plus a minus 1. That's going to give us a 12. So we look up on the periodic table for an atomic number of 12. We have Mg. Okay, so those are some examples of writing nuclear equations. The next thing I would like to do is look at an example of doing a half-life calculation. Now, this is not new to this chapter. We have done half-life calculations in the kinetics chapter, and we did kind of a more involved example there. This one, it turns out, will be a little bit simpler, but you need to be able to do either style of these. So let's go ahead and read the question. The half-life of iodine 123 is 13 hours. How much of a 64 milligram sample of iodine 123, that's iodine 123, is left after 26 hours? Okay, so let's go ahead and write down some things we know here. So the half-life is 13 hours for the iodine 123. One thing I'll mention, just so you're aware, with these types of half-life questions, the identity of the substance doesn't come into the calculation. So the iodine 123 in the type of question we just did with the nuclear equation, it's very important to take that 123 into account, take the iodine, the fact that it's iodine into account. But for the purpose of this question, the only thing we need to know this for is if we were not given the half-life, we would look it up and see that it's 13 hours. Now, I'm not going to have you do that. I'm going to give that to you in the question. But the 123, we're not going to do a calculation of 123. And then we have an initial amount. I'm going to call this A naught is 64 milligrams. And then we have a final time of 26 hours. Okay, that's the information we're given that is relevant to this question. Now, one thing you might want to do when you see a half-life question is just check if you can do it the easy way before doing it with natural logs. And for that to work, for it to work in the easy way, what you want to check is, do you have an integer number of half-lives? If you do, then you can do it the easy way. So in this case, we have a half-life is 13 hours and our time is 26 hours. So we can say our time is equal to 2 times 1 half-life. It took 2 half-lives to go to 26 hours if 1 half-life is 13 hours. Now, if we were given 27 hours, we couldn't do this, right? So it only works if you happen to land on exactly an integer number of half-lives. In this case, we have 2 half-lives. So how this works is, in a half-life, we lose half of what we have. So we can say, okay, we're going to divide by 2. So if we start with 64, we divide by 2, we get 32 milligrams. That would be 1 half-life. And then we do that again, and we get 16 milligrams. That is 2 half-lives. Okay, so our answer here is 16 milligrams because we have 2 half-lives. If we divide by 2 twice, we get 16. So that's how we got to that. Again, this only works sometimes. Some of the time you'll have to use the natural log method that we covered in the kinetics chapter. So that is it for this video. I just wanted to cover a few examples of calculations with nuclear equations and with half-life, so that you're kind of up to speed on that as we discuss the rest of the chapter.